Okay, I think we're in business now. So let's take roll. Let me so I can see the names. All right, answer your names, please. Albright, Karen, Champ, here. Chavez, I think, is here. Heroes, here. Johnson, here. Jones, here. Martin, Malloy, here. Mohammed Boy, here. Olson, Richardson, Sisson, who's here, Varney, Vasquez, here. And Weflin. Okay. Albright is here. Can you guys over there in Zoom hear me? Oh, okay, thank you. All right, so let me share my screen here for the benefit of those guys out there. And today, the topic of discussion will be chapter 3. Okay, chapter 3, which deals with matter. And of course, I'm going to make the assumption that you'd have already watched the video, which covered chapter 3. It's a relatively short chapter, and the topics there are relatively easy to understand. Before I do that though, a couple of announcements. So assignment number 2, it's due today. If you don't have it to turn in now, you can turn it in online. If you plan to turn it in online, make sure that you do that. You submit it as a PDF document, all right? Make sure that your name is also on the assignment as well. So it's due tonight at midnight. That's the first thing. The second thing I want to talk about is an announcement I've already posted in Canvas concerning the STEM Club. If you're so interested to join, our first meeting is tomorrow at 12:30, and I think I included in the announcement the Zoom link for that, so you can join the meeting. If you're so interested, I know most of you who are doing, science courses, especially chemistry, are planning on pursuing careers in medicine, pharmacy, and the health sciences in general, but there are also other options, career options when it comes to, the STEM fields, which you might find to your liking. So please, if you are interested, you can join up. And we plan a lot of activities, which include field trips to different facilities. We'll have speakers coming to talk to the group concerning their own career choices in STEM. There's I don't know, workshop would not be the word. It's more like a conference, the STEM Summit, which would be, if I remember correctly, in April. And again, that will include speakers and panel discussions and so on. And most importantly, one of our aims in the STEM Club is for the members to engage in some sort of research activity in the form of internships. That's very important, especially if you're considering going to grad school and all that. It will really look good on your resume if you show that you have actually participated in some research activity as an undergrad. So, those are just some of the benefits involved if you're so interested. So, as I said before, the first meeting will be tomorrow at 12:30 on Zoom. And one of the first issues that we have to deal with is selecting leadership, the president, vice president, and other members of the executive. So just thought I should let you know about that if you're interested. All right, so with that out of the way, let's talk about matter. I'm just going to go through this briefly because, as I said before, this was already covered in the videos that I've posted online. And basically, matter is anything that has mass and volume, and it is basically the stuff that makes up anything material. And one important concept of matter that you need to be aware of is this whole concept of properties. When we talk about the properties of a substance, we're talking about the type of defining characteristics, right? So we're talking about things like color, taste, density, melting point, boiling points, all those things which help you to identify a particular substance. Each substance has its own unique set of properties. So for example, water is a colorless liquid, has a boiling point of 100 degrees Celsius, a freezing point of 0 degrees Celsius, has no taste, and so on and so forth. What I've just said is basically a set of characteristics associated with water, and therefore what I've just described is a set of properties of water. As far as properties are concerned, there are two types. You have physical properties and chemical properties. And physical properties are basically properties that one can observe without changing the basic nature of the substance. In other words, these properties can be observed without the substance undergoing any chemical reaction or chemical change. So what you see here on the screen is a list of physical properties associated with water, with any substance, water, whatever. Some of them are qualitative. In other words, you can't measure them, but you can describe it, such as taste and color. And then others you can measure, like the melting point, boiling point, densities, and so on. So for example, if we take chlorine, these statements are true for chlorine, and these are all describing certain physical properties of chlorine. The fact that chlorine is more dense than air, it has a yellowish green color, its odor is disagreeable, has a melting point of minus 101 degrees Celsius, and a boiling point of minus 34.6 degrees Celsius. All right, so those are basically some descriptions that are associated with chlorine. So that's as far as physical properties are concerned. Now, chemical properties are those properties that, when observed, involves the substance undergoing a chemical reaction. All right. So in the case of chlorine, going back to chlorine as an example, what I'm showing you here are some characteristics of chlorine, some properties of chlorine. Will not burn in oxygen, but it will support the combustion of certain other substances, can be used as a bleaching agent, it can be used as a water disinfectant, and finally, it can combine with sodium to form sodium chloride. So what you're looking at here is basically a select few properties displayed by chlorine, which would fall under the category of chemical properties. So every substance has their own unique properties associated with them. We talked about chlorine, and what you see on the screen are some other substances and their select properties, physical and chemical. All right. And that's as far as that is concerned. Now, if you understand what I just discussed with respect to physical and chemical properties, then you should be able to understand what we mean by physical and chemical changes. It's basically the same underlying principle. So when we talk about a physical change, we are talking about a change in the physical properties, but the matter itself or the material itself does not undergo any change in composition. For example, tearing of paper, changing ice into water, change of water into steam. These are all examples, heating platinum wire. These are all examples of physical changes. And what they all have in common is that there's no creation of new substances, all right? So that's basically what we mean by physical changes. Chemical changes necessarily involves a chemical reaction. In other words, whatever the result is after observing these changes, the products will be different from the reactant. So for example, if you heat a piece of copper in air, then what will happen is that you'll notice that the copper will change from its usual reddish brown color to something black, right? And the reason why that happens is that when you heat it, the copper reacts with oxygen to form a new substance, which is copper 2 oxide. And we know it's a new substance because it is different from the old substance by virtue of the fact that it has different composition, right? So copper by itself is obviously 100% copper by mass, but copper 2 oxide is a mixture, or I should say a chemical combination of copper and oxygen, and the compositions are shown there. So therefore, the copper 2 oxide that is formed will have a completely different set of properties compared to the copper from which it is formed, all right? So that's what we mean by chemical change. A new substance is created. Let me just skip all this here and talk about how do we represent a chemical change. And in chemistry, we have a shorthand way of representing it by using what we call chemical equations, which we won't talk about much in this chapter. We're going to deal with it in greater detail later on. But basically, in a chemical equation, we have on the left side the reactants. Then we have an arrow, right, which basically means produces or yields. And then on the right side, we have the products. Now we can actually write down the names of these substances, but in most chemical equations, we actually write down the formulas, and therefore we use chemical symbols that represent the formulas for the different substances. So the formula of water is H2O. The formula, in this particular case, we're talking about, I should have said this before, we're talking about the electrolysis of water. I don't know if I mentioned this before, but electrolysis is basically using an electric current to pass through a substance, and the result of that is that the substance breaks down into simpler substances. In this case, we're breaking down water into hydrogen and oxygen, all right? So what you're looking at here is basically the chemical equation that is used to represent that change, all right? And there are certain things that you need to do in order to ensure that the chemical equation accurately represents what is happening, but we're going to get into that later on. We won't talk about that now. Here's another example, the reaction between copper and oxygen to form copper-2 oxide. The equation that we use for this is this right here, right? Again, it shows you the reactants on the left side, the products on the right side. And in this particular case, we have a symbol here, a small triangle. That is conventionally the symbol we use to represent the fact that we're heating the reactants in order to ensure that the reaction takes place. So there are some reactions which require heat in order for the reaction to take place, all right? So here are some examples of physical and chemical changes. So usually when you're given a question in a test or quiz or, well, test or exam, you might be given something happening and you're to tell whether or not a chemical or physical change is taking place. The main thing that you need to remember in order to distinguish between the two is that in a chemical change, you're converting from one substance into another. The product will be different from the reactants. The product will have a different composition compared to the reactants. The products will have different properties compared to the reactants, all right? That's what happens in the case of a chemical change. In the case of a physical change, there's no change in the composition of the substance that is undergoing the change. So for example, the second line here deals with boiling water. When you boil water, you're converting the water, which is in a liquid state, to water in a gaseous state, all right? But it is still H2O, right? The composition does not change, all right? Basically, you're changing the state, whereas initially you're starting with liquid, and then in the end, you're going to end up with a gas, all right? So that's an example of a physical change. Chemical change, such as the first one, rusting of iron, that's definitely chemical. Why? Because you're starting with a metal, which is iron, and then the iron will react with moisture and oxygen to form a new substance, which has a reddish brown color, which is known as iron 3 oxide, all right? So in the assignment I'm about to give you, there are some questions which actually deal with identifying a particular process as being either chemical or physical. Okay, one more thing I want to talk about, or maybe this is not the last thing, but one thing we need to talk about when it comes to chemical changes, or any change for that matter, is that there's a law known as the law of conservation of mass, which basically states that there's no change in the total mass of a substance in a chemical change. In some textbooks, you'll see it worded as the mass in a chemical reaction is conserved, means the same thing. So basically, whatever the amount of material that you start off with, the mass of the material that you start off with will be equal to the mass, the total mass of the products that you end up with. So as an example, let's say we have a reaction between sodium and sulfur. If you react these two, you're going to end up with sodium sulfide. And if you actually weigh the amount of product and compare it to the original amount of reactant in terms of the mass, you'll see that there's a conservation of mass occurring where the total mass of the product will be equal to the mass of the reactant, all right? So that's basically what the conservation of mass is all about. Some other topics covered, elements. Elements are basically substances that cannot be broken down into simpler substances, while compounds can be broken down into simpler substances. And then we talked about mixtures and pure substances. A mixture is a physical combination of two or more substances, and mixtures can be put into two subcategories. One is homogeneous and the other one is heterogeneous, right? Homogeneous mixture is basically a uniform combination of two or more substances. So basically you cannot make a distinction between them in terms of looking at it. So for example, if you add salt to water and you mix it, all the salt dissolves, that's a homogeneous mixture because you cannot distinguish between the salt and the water in that mixture. Some other examples are provided here, sugar and water, and I'm quite sure you can name some other examples as well. And then we have heterogeneous mixtures, which is a non-uniform physical combination of two or more and substances. And some examples are shown here. If you mix sugar and fine white sand together, basically you can make a distinction between those two by just looking at it. Another example is oil and water. I'm quite sure we all know this. If you take vegetable oil and add it to water and you stir it, then what will happen eventually is that there's going to be a separation between the two layers, where the top layer would be the oil and the bottom layer would be the water. All right, now, the last slide here is asking some important question, because in chemistry, and this is true from, facilities such as our own labs here, where we do, basically academic lab courses where we perform experiments, and up to the more sophisticated facilities. One common problem that is faced by chemists all over is separating a mixture, all right? And basically, in order for you to separate a mixture of two or more substances, you have to basically identify some difference between the substances in the mixture in order to separate them, all right? So here we have some situations here, and these are relatively simple problems that you're asked to solve. The question is, how would you separate the following? Salt from a salt solution, a mixture of salt and sand, ethanol and water, and oil and water, all right? So let's start off with the first one. How would you separate salt from a salt solution? Yes, sir.
Filtration.
Filtration. Don't go seriously, that would work. Can anybody tell me the reason why that would not work? Because it's a homogeneous mixture, right? If you try to separate by filtration, everything is going to pass through the filter, right? So you'd only use filtration if it is a heterogeneous mixture, and only if it's a combination of, let's say, a solid and a liquid, all right? So back to the question, how would you separate such a solution? Yes, ma'am. Exactly. If you boil a solution, what you're exploiting in that particular case is the difference in boiling point between the salt and the water, right? Water has a boiling point of about 100 degrees, and salt has a boiling point which is much higher. I don't know what it is, but it's definitely nowhere near to 100 degrees Celsius, right? So when you heat that solution, what's going to happen? The water, the liquid water, will vaporize, right? Escape as a vapor, and the salt will remain in the solution. Or not in the solution, but in whatever the container it's in, all right? So that's basically how you separate such a solution. The next is separating a mixture of salt and sand. How would you separate such a mixture? And I think that's where what you suggested will come into play. So let me hear some suggestions. A filter, right? In chemistry, oh, let me draw it on here for the benefit of the students. I forgot. There are students out there in Zoom. So in chemistry, like in our labs here, we would use the following. Let me get rid of this here. We would use a funnel. And please forgive me, I'm not blessed with the perfect artistic skills, so this is going to be very, very rough and maybe painful to the eyes. Okay, so we have a funnel here, right? And then I'm going to put in it a filter paper. Now, for those of you who have to do General Chemistry 1, and if you're going to have me for General Chemistry 1, you'll definitely be doing some of this, all right? We have a funnel, we have the filter paper. So this here is the, whoops, this here is the filter paper, all right? So you're going to pour your mixture. So the mixture, as we said before, is salt. Well, actually, before you do that, I forgot one important thing. We need to do something before we use the filter paper or the filtering system. What we need to do is add water to your salt and sand mixture, all right? So this would be, the result of that would be the salt solution, right? And you're going to have your particles of your sand, right? So the first thing you need to do is dissolve the salt, right? You add water to it, dissolve the salt, and in that particular case, you're exploiting the difference in solubility of salt and sand in water. The salt will dissolve, the sand will not. So here, you're going to pour in this mixture, or pour this mixture into the filter paper in the funnel, the salt solution, and the sand. And what's going to happen? The sand is going to be trapped on the filter paper, and the salt solution will pass through. So you're going to end up with your salt solution. And the technical name for this solution in this process, this is called the filtrate. All right. So basically, you'd have isolated the sand. This is your sand right here. And then all you need to do now is take the solution, and you're going to heat it as we described before. So this is sodium chloride solution. And you're going to heat it. And of course, the water vapor will leave, and you're going to have the sodium chloride solid left behind in that container. And that's basically how you'd separate a salt and sand mixture. All right, so that's the second one. The third one is a mixture of ethanol and water. And let me just say that this mixture is a homogeneous mixture, all right? If you mix ethanol and water together, you'll have one phase. You won't be able to distinguish between the two, all right? So my question is, how would you separate such a mixture? You boil it again, but you have to take some extra precaution because you want to end up, at the end of this process, you want to end up with two containers, one containing the ethanol, the other one containing the water. So how would you make that arrangement? Yes, ma'am. Very good. So as you said, you heat the mixture, right? The water vapor will leave. And the reason why the water vapor would leave first is because the boiling point of water is 100 degrees. And if I recall, the boiling point of ethanol is about 78 degrees, right? So because of that difference in the boiling point, actually, it's the ethanol that will leave first. My mistake. The ethanol will vaporize first. So it's kind of, to what you said, you'll have to find some way of condensing the ethanol vapor, not the water vapor, right? And then you'll end up isolating both the ethanol and water. Now, in chemistry, and this is for those of you who have to do organic chemistry, there is an apparatus set up known as distillation. And for those of you who may be involved in the illegal activity of moonshining, then you probably know about this. But basically, part of this apparatus involves a flask like this, and it will be heated once you have your mixture in here. So this is a hot plate. And then, so you're going to have your mixture in here. So let's say your mixture is ethanol and water, all right, H2O. This will be connected to an adapter here. And then this adapter here, oh, this is looking awful now. This adapter here will have a stopper here, which may or may not have a thermometer. So I'm going to include a thermometer down here. So this is the bulb of the thermometer. This outlet here would be connected to a condenser, which has an inner glass tube. And then surrounding it, there's an outer jacket, which is also made of glass. Okay, looking like this. And then this has another adapter connected here. And then you'd have a flask or some other container, which is allowed to collect your distillate here. Okay, so as I said before, you're going to heat this mixture here. And as I said earlier, the ethanol vapor being of a lower boiling point will start emanating from the surface of the mixture. We'll go up here, hit the thermometer so you can measure the temperature. And then the vapor will travel down this inner tube here. Now, one thing I should have mentioned is that the outer tube surrounding the inner tube will have two outlets. This will be connected to your water source, so H2O in, and this will be connected to a hose which would lead out into your sink. So water will be coming out here. So basically what's going to happen is that the outer jacket will be basically having water flowing through. So basically the inner walls here would be cooled such that when the vapors hit the inner walls, then the vapor will be condensed to liquid. So you're going to have droplets of the ethanol being formed here, right? So that's basically how the vapors of the ethanol is being trapped, and they will roll down here, and then you're going to collect it in your flask right here. So this will be your ethanol, and the name given to the liquid collected in this experiment, we call this the distillate. All right. So basically that's the setup, and the temperature here that would be recorded would be the boiling point of ethanol, which if I remember correctly is approximately 78 degrees, all right? So basically that will continue. The temperature will remain at 78 degrees as long as you have ethanol emerging from here. When all the ethanol has evaporated, then you only have water, and then the temperature is going to rise again until you get to the boiling point of water, and then the water vapors will start emanating. So you'd have to switch this flask right here and put another one here to collect the water. And as a result, you'd have achieved the separation of the ethanol and water, all right? So that's basically the distillation. And this is called a simple distillation apparatus. You have some that are more complex because in some situations, not all mixtures of this type can be separated using what I just described. If the boiling points are closer, then you'd have to add another piece to the flask right there and use some inert material in that tubing. And that is called fractional distillation. So that is used if the boiling points of the liquids in the mixture are closer. This is used if the boiling points of the liquids in the mixture is about 20 to 30 degrees difference. If the difference is smaller, then other modifications would have to be made. You have simple distillation, which is what we described. You have fractional distillation. You have, I think they call it low pressure distillation. You have different types. It all depends on the mixture that you're working with, all right? So that's basically how you'd separate a mixture of two liquids that are in a homogeneous, homogeneous with each other. Okay, the last of this series of questions is how would you mix, or how would you separate a mixture of oil and water? How would you separate a mixture of oil and water? Any suggestions? Now, oil and water, of course, is heterogeneous, all right? So how would you achieve such a separation? Okay, you could do that. So you're saying that because you're going to have two layers, you could use like a syringe to pull up, let's say, the top layer continuously until the bottom layer. You could do that. One convenient way of doing that, and for those of you who have to do organic chemistry, you'll be doing this a lot. You use what is called a separator funnel. Separatory, hope I'm spelling this right, funnel. Now, this is more convenient than what you described, and I'm going to show you why. So a separator funnel, again, please forgive my poor artistic skills, but they come in different shapes and sizes. So this is my interpretation of what a separator funnel looks like. And down here, you're going to have a tap, and then an outlet right here. So let's say you have a mixture of oil and water poured into here. So the oil would be at the top, and the water will be below. And all you have to do is put something here, of course, to collect what is coming through. Open this up, and you allow the bottom layer to drain into your container until the boundary between the two gets to where the tap is, and that's it. Then you turn it off, and that's it. All right. So that's more convenient than what you described, even though what you described would work. All right. So as I said before, this is used a whole lot in organic chemistry, where you have to separate. Usually in organic experiments, you'd have one particular substance here, another particular substance here, and you'd have to basically separate it this way so that you can take care of each solution and carry out the rest of your experiment. Okay, so I just thought I should go through that so you have a feel for, the type of things that is done normally in a chemistry lab. All right, so this is just a summary of the different types of mixtures that we talked about. I don't need to go into that again. So what I'm going to do now is give you assignment number 3 to work on, which is based on chapter 3. And if you have any questions, feel free to ask. That's what I'm here for. You put that down. 1, 2, 3. Take one of that. And for those of you out there in Zoom, I am going to publish it. I think I may have published it. Let me check and make sure. So assignments, and this is chapter 3. Okay, so now it is published for those of you out there in Zoom, so you can get started on that now. And if you have any questions, feel free to ask. Yes, ma'am. Mm-hmm. Here that we breathe. What question is that? So, okay, number 1 here, right? So the air we breathe is a mixture of mainly nitrogen, which is about 78%, and then oxygen, which is about probably about 20%, and then we have some minor gases. And when it comes to a mixture of gases, they are all homogeneous, right? You'll never have a mixture of gases where you have a separation between the different components. It's all homogeneous. So the air we breathe is a homogeneous mixture.
The nickel one.
Okay.
Is it a modern nickel or an old nickel?
So when it says any nickel, to me, I would interpret that as the coin and not the element.
Yeah, but like back then, the coins were like pure nickel, but now they're like now they're a mixture of nickel with something else.
It's called, right. So when it comes to metals mixtures, there's a special name for that. They call them alloys. right? So nickel would be an example of that. So that would fall also under the category of homogeneous chemistry. Exactly. Exactly.
Can't see what's nickel and what's green.
Right, exactly. Let me see if I've gotten everybody's attendance. Is Karen here?
Yes.
Oh, okay. Olson. Let me check over here. Wetland.
Here.
Would cheese be considered the same substance?
I'm sorry?
Would cheese be considered the same substance as milk?
Yeah.
Like bacteria.
Yeah. And in the case of milk, that would be, even though, and this is a tricky one, even though one might think it's homogeneous, it's actually heterogeneous. And the main reason why is that if you look at it, especially like from a microscope, you see some dispersed in the middle, you see some smaller sacs of fat. See what I'm saying? So therefore, strictly speaking, that would be a heterogeneous.
Metal lens referring to rust metal.
I'm sorry.
Question two, part C, version of the metal, you're referring to rust, right?
Yeah. So you're talking about question, this one?
Yes.
Right. So what do you think that is? Physical or chemical? Exactly.
So very hard to see.
Well, it's kind of similar to the rest.
Okay.
Yeah.
Is there a difference?
except in that it's iron in one case and silver in the other case. In both cases, they're forming oxides. Yeah.
What is the first worksheet as a PhD? No, it's like those.
No, and the only reason why is because those are very difficult to download for some reason from Canvas. It's very difficult to download. So
Does that mean I'm gonna get 8 points?
no, I mean, if you can resubmit it as a PDF, I'll take it. Yes, ma'am.
Would diamond be a compound?
No, diamond is a form of carbon, which is an element. Yeah, there are different forms of carbon. Diamond is one of them. Another is graphite. Another one is, there are several others, but it's an element, not a compound.
Or physical property?
What's that?
Mass is considered mass is considered a physical property.
No. Gasoline is a mixture of hydrocarbons. So therefore, what question is it?
Was 7 and 1.
Hold on. Did I pass it?
7. On ours,
You mean here?
yeah, the gasoline.
Where's gasoline? Right. Oh, so they're asking to put it in, okay, so that would be a mixture, definitely. Right. Gasoline is a mixture of hydrocarbons.
Would it be hetero?
Well, ethanol is an additive. You know what I'm saying? You can't put, you certainly can't put ethanol in, or just ethanol alone in an engine. As far as I know, I don't think they have developed an engine that works on just ethanol. Yes, ma'am.
What is dog?
What do you think?
Probably like. A compound?
Oh. Exactly.
I thought it would be.
No, it's a mixture. Certainly a form of matter. Hold on, somebody has a question from Zoom. But yeah, dog would be a mixture. Somebody, let's see what this question is. Oh, so, Wetland, you're here, okay. Good question. Anybody want to help her out on that one? It will be none, because for one, it's not material, right? Remember, we said that by definition from very early in the PowerPoint, matter is anything that has mass and volume. Energy has neither. So you would even, that would be what, the X you put there?
The lustrous metal,
I'm sorry?
the lustrous metal,
Where is that?
question
Question 3.
3C.
Question 3. Oh, meaning shining. I'm sorry. Right. Mhm.
Is electricity also an X?
Yeah. For the same reason. Yes, ma'am. If you're confident in your responses, you can turn it in today if you prefer. Now, before you leave, let me let you know that for your next class, you need to watch the videos. I'm going to publish it right now for chapter 4. So let me scroll down here. Let me expand this and let me publish that. So make sure that you watch these videos dealing with elements, atoms, and so on, chemical compounds and chemical formulas, all that good stuff. Make sure you watch those videos. If I'm not mistaken, the last link is kind of lengthy. So hold on, let me check. Oh, no, actually, I was thinking of chapter 5, actually. Okay, so yeah, that should be a relatively short chapter. So make sure you watch those videos. If you have any questions, feel free to contact me during my office hours concerning that. Yes, ma'am.
Acts with certain substance that automatically means chemical.
Exactly. Mhm. Okay, so, oh, and by the way, if you have assignment 2 as well, I'll collect it. So this is chapter 2, and we have the chapter 2 assignment right here. Yes, ma'am.
I have some questions for chapter 2.
Okay.
For question B,
Okay.
I was kind of confused on how to do that.
Okay, so in the case of C, Bessie, if you look in the table, in the chart that I've given you, you use a pencil. If you look in the chart that I've given you, you'll see that the prefix Deci means 0.1 or 10 to the minus 1, right? So basically, you start off with the 25.0 liters, and I would multiply by the appropriate conversion factor, where you put 1 liter down here, and I'm sorry, 0.1 liter here, and 1 deciliter here, right? Because deci means 0.1, all right? So the liter unit will cancel out, and your answer here would be equal to the unit of the deciliters, right? So therefore, that would be 250, decimal point here, deciliter would be the answer. And you do a similar thing in the case of B. Pico means 10 to the minus 10, right? I'm sorry, 10 to the minus 12. 10 to the minus 10 is 11. So, no, 10 to the minus 9 is 11.
It is 9, yes.
Yeah, 9 is 11, right. Yeah. Anyway, so I would start with a 0.010 grams, and I would multiply this by, so pico is 10 to the minus 12, right? So I'll put 10 to the minus 12 grams down here, and 1 picogram right here. And when you work that out, that would work out to be 1.0 times 10 to the minus 10. I'm sorry, 10 to the 10. Sorry, 10 to the 10. Picograms. That's it. Right? So what I would strongly recommend is that you set up all your solutions like what I did here. Show the conversion factor, which shows you the relationship between the units that you're working from and the units that you're working to. All right? That's it.
Thank you.
No problem. Yes, sir.
What's the difference between flammability?
Not much of a difference. Same thing actually. So they're both chemical.
Same factor, was it compound?
Right.
Element. Compounds are just.
Right.
Things that are,
Right.
nothing super complex.
Right, a compound is basically a chemical combination of four elements, and the thing about compounds is that their composition is always fixed. Right, so like water is always going to be, if I remember correctly, 18% oxygen and the rest will be hydrogen. Right, that's basically all compounds. Mixtures, the composition can vary.
So the charge is the equivalent to iron rusted, right?
Exactly, so that would be a chemical change.
So that's not the sours.
Again,
Why is the souring mixture?
because it's a reaction where, if I remember correctly, lactose, which is in the milk, is converted to lactic acid. So this sour taste is due to that lactic acid.
So would an apple be oxidative count?
Yeah, whenever you cut open an apple and you leave it exposed to the atmosphere, It's a chemical change when the color changes. So that's an oxidation that, yeah. Yes, ma'am.
Frost.
Is something what?
Frost.
Yes, yes, yes. That's right.
So an apple is cut is.
No, if the apple is cut, that would be physical. What I was talking about is it when it left exposed, then, you know, the change in color that you see, that would be due to, that would be a chemical change.
Right.
But the cutting itself would be physical.
And wood rotting is also a chemical.
Right.
Wood rotting is chemical.
Yes, yes, definitely.
Pancakes cooked.
Hmm?
Pancakes cooked would be chemical.
Exactly. Yeah,
I thought,
Because the ingredients in the pancakes are reacting together to make it ready.
if it said like cooking, well,
yeah, if you're cooking, pretty much if you're cooking anything,
You know,
it would be chemical.
if you're just heating something up, it's not cheap, but if it's like not made yet.
Well, in some cases, the heat will actually accelerate whatever the process is, chemical processes. So even something as simple as boiling an egg, that would be a chemical change as well. You're actually changing the structure of the proteins in that situation. Yes, ma'am.
the alcohol evaporate water is still water, it's still alcohol.
Exactly. Just simply evaporating is a change from liquid to gas, but there's no change in the composition of the substance, so that will be physical.
For number 1C, it says magnesium. Is that an element?
Yep.
Okay.
So it's manganese. So in all the elements that you see there on that periodic table over there.
So it'd be like counted as a pure substance because it's an element.
Well, a compound can be a pure substance. The difference between an element and a compound is that you cannot break down the element into anything simpler by chemical means, right? So like, for example, magnesium, you cannot break it down into anything simpler, or carbon, or sodium, or selenium. But a compound like water, you can break that down into something simpler. You can actually break it down into hydrogen and oxygen. Or if you have, let's say, carbon dioxide, you can break it down into carbon and oxygen, right? So that's the difference between the element and a compound.
Mm.
Right?
Or two chemicals are mixed together and a gas is produced, that would be chemical, right?
Same, like,
Mhm.
like. For that one, like right below it says two substances are mixed and light,
That's chemical.
even though light.
Yeah. Sure.
Oh, thank you.
Would the marshmallow composition of the campfire be similar to the pancake or?
Right, so that will be chemical.
I'm not sure.
You should take care.
Element, right?
Mhm.
Krypton is an element.
Yep. Oh, yes, that's group 8. The periodic table. Yeah,
Basically, anything that is a living organism.
exactly. Okay, which one is that? Okay, that was it.
Ice is a compound.
Sorry,
Dry ice is a compound.
yes. The dry ice is actually frozen carbon dioxide.
Isn't that like incredibly painful to inhale?
Oh, yeah, you don't want to consume that.
Or touch it,
Well, you can touch it, but
dry.
yeah, but you don't want to, inhale it or, because carbon dioxide is toxic.
So it's toxic.
I'm sorry?
No.
Yeah, it's made of mixture of hydrocarbons.
Bronze, is it sure? Bronze,
Yes, it's a mixture of metals. I don't remember what the metals are. But I know it's a mixture of metals.
baking soda and compound. With
Exactly, compound. That's sodium bicarbonate.
take salt,
That's right.
salt is also a compound.
Sodium chloride, yeah.
Sulfuric acid is a compound.
Sorry.
Sulfuric acid is a compound.
Yeah.
Basically, for that one, if it has parentheses and two elements, it's
Right. That's why the formula is given.
Ink would be a mixture.
Yep. No, what is an element? So, yeah.
I still technically at 15 minutes, right?
Yeah, yeah, I mean, I'll just hang around until time. Yes, man, take care.
I got like two questions.
Good lunch and then have a go. Ooh. Yes, sir. Okay, for you guys out there in Zoom, I'm shutting off right now. I'll see you guys next week, Tuesday, all right?